Yeah. So this is a big talk. And so my topic for today is going to be on the principle of inclusion and exclusion, which is usually abbreviated to as just PIE. And that's just for short. Some people just directly say pi, although that's just not clear enough. And so this is like a basic overview of PIE. So this is the case for two. This is the case for like two cases. So if you don't know, so what PIE counts? So basically it says that you can see it here. So basically the number of stuff that's in this stuff that's sorry. The number of stuff that's being counted in here is equal to the number of stuff in here plus the number of stuff in here minus the number of stuff in here. And so the reason for that is because let's say that something's only in yellow, then it's counted once in here. And if something's only in blue, then it's counted once here, and it's only counted once because it's once here. But if something is here in green, then it's being counted twice because once in here and once in here. So then you have to subtract that one for the middle area to also be counted exactly one time. And of course, this pattern can continue on, but for most intents and purposes, this is about sufficient. So here is an example problem for this topic. So everyone can like look at it for like 1 minute or so and try to do this. Okay, so I'll assume all of you have had some time to try this one on your own. So you can see that it's either, ouch. Okay, so it's either computer science or math or both. So the number who have CS as a major is 25. And the number who have math as a major is 13. And the number in both is 8. So that means that we can look at this theorem above, well, this statement of PIE above. And so that basically tells us that the number in the class is equal to the number taking CS plus the number of math minus the both. Okay. And so that means that we can just see that the answer is just 25 plus 13 minus 8, or 30 students. And yeah. Any questions? Okay, well, I guess there are no questions. So I'll just go on to the next one. So this is the formula for PIE in general. So in general, so basically the number of elements, okay, so the number of stuff, which I'll just call elements from now on because that's how it's what is called in math. The number of elements total in n sets of stuff AI is this fancy thing, which is basically just saying that it's basically just, so I'll just explain this in a more intuitive way with just some lower number examples. So let's say there's sets A, B, C. So then it would be A plus B plus C minus AUB minus AUC minus BUC plus A cup B cup C. And so that's how PIE works for 3 numbers, and for 4 numbers it would be this is about the same, except that it would just be, sorry, A plus B plus C plus D minus A cup B minus A cup C minus A, oh, it's cap, sorry, not cup, A cap D minus B cap C minus B cap D minus C cap D plus A cap B cap C plus A cap B cap D plus A cap C cap D plus B cap C cap D minus A cap B cap C cap D. And so this long thing is just PIE for 4 numbers with A, U, B, U, C, U, D. And I guess this is probably slightly more intuitive to understand than what's written here, but like this is true in general. So, yep. And so next we have another example. And so this involves PIE with some more variables. And so I'll give all of you a minute or so to try this on your own before I go over it. Okay, well, that should be about enough time to get a start on this problem. So we can see that there are 8 people total, and basically the important part is no one received their gifts back. And so we want to find the number of ways to distribute the gifts. So, sorry. So we can let set, let's say, A be the number of ways to distribute the gift such that everyone gets a gift. And this does not care if they get their own or not. And so now we let AI be the set of ways someone person number I gets their own gift. And so what we're trying to do is find this. So since AI is the number of ways for person I to receive their own gift, that means that there are 7 factorial ways for the rest of the gifts, and that's because there this doesn't us saying that person I gets their own gift does not affect whether others get their own gift or not, because he got his own gift. Now, if person I did not get his own gift, that would mean that someone else also did not get their own gift. But since we know that person I got their own gift, it doesn't matter affect anything else. So yeah, so AI is equal to 7 factorial, and if both person I and person J for some 2 different people I and J, then there are 6 ways to choose 6 gifts for the third person, 5 gifts for the fourth person, and so on. So it's 6 factorial for here. And we can see that this just continues on 5 factorial, 4 factorial, so on. So this means that the number of ways to distribute the gifts is just, once again, as a reminder, it's A minus A1, U A2, U all the way to U A8. And this is equal to 8 factorial minus. And so here we have 8 times 7 factorial. And now we add 8 choose 2 times 6 factorial. And the reason it's 8 choose 2 here is because there's 8 choose 2 ways to choose the pairs. Because if you remember, the pairs need to be in ascending order or descending order. It doesn't really matter as long as each distinct pair of A's is counted exactly once. And so on. So there's also minus 8 choose 3 times 5 factorial, and so on until the final term is 8 choose 8 times 1 factorial. And I don't think anyone wants to see the calculations being done because they're not fun. So I'll just say that the answer is 14,883. And just a fact related to the name enriching here. So derangement is basically just this number is basically the sole problem. It's basically just derangement. So derangement just basically is something where where a set of values is where the order of the values in a set of values is changed around, and the number of ways that a derangement is just one possibility of the permutations such that no objects stay in the same place. And so what we found here is the number of derangements of 8 objects. Okay, and so now okay. All right, so I'll be starting to go over this problem now. So there's a unit square of a 3 by 3 unit square grid, and all of them are either blue or red. So each color is equally likely. We want to find the chance of a grid that does not have a 2 by 2 red square. So first of all, what you can realize is that this is a 3 by 3 grid, which looks something like this, although probably with a lot straighter lines. And so there's only 4 ways to have a circle, a 2 by 2 square, and their centers are the intersection points that I circled just now. So each has a probability 1 over 2/4 of occurring. Now there are a total of 6 possible intersections, and so 4 of them have probability 1 over 2/6 because they are intersections of this sort. Okay. They're intersections of this sort. And others have a probability of 1 over 2/7. 4 of them have 2/6, and 2 of them have 1 over 2/7. The ones that form 1 over 2/7 are of this form. Yep. Okay. So now we need to add the probability that there's 3 of them together, which is always 1 over 2/8, and there's 4 possibilities here. And so the last case is when the entire grid is red, which is all 4, and this has probability 1 over 2/9, and my PIE is being subtracted. So, yeah. So now if you calculate all of this together, then what you get is that this is equal to, I believe, 95 over 512. However, this is the opposite of what you want because this is the probability of a red square, but you want the probability of not having a red square. So 1 minus this is just 417 or 512. And of course, like Amy formats, it says it's in the form of or n, and then it wants n plus n. So it's just 929. And so that's this question. So next up, we have this question. And so once again, I'll be giving a minute or two for people to try to figure this out on your own. Okay, so I think that's enough time. And so I'll start going over this now. So there are 3 delegates from 3 countries, and they're choosing chairs around a round table. So we want to find the probability that each delegate sits next to at least one delegate from another country. So first of all you do is basically we're going to use complementary counting and PIE, just like the last problem. So we can consider the delegates indistinguishable. Yes, I know that usually you consider humans distinguishable, but it doesn't really matter. It's just they're just different countries. So now the number of ways to see the candidates, that means is just 9 factorial over 3 factorial cubed. And so this is just 9 times 8 times 7 times 6 times 5 times 4 over 6 times 6. And so the value of this is simply just, if you calculate it out, this is just 1680. Yeah. So next, there are 3 times 9 times 6 factorial over 3 factorial ways, 3 factorial squared ways for the candidates for all 3 candidates of a country to sit together, which is the only case where some delegates does not sit next to at least one delegate of another country. And so the probability of this occurring, the number of ways for this occurring is just this number, which is 27 times 6 times 5 times 4. Oops. 27 times 6 times 5 times 4 over 6, which is just 540. So the number of ways for 2 candidates from 2 countries to sit together is just 3 times 9 times 4, which is simply just 108. And finally, there are 9 times 2, which is 18 ways for candidates from all the countries to sit in 3 blocks. And in case you're wondering what's going on and why we just ignore the fact that it's circular, we're finding a probability in the end, so everything will be canceled out, so it's fine. So technically this works for a linear line too, but yeah. I don't know, this does not work for a linear line, but anyways. It works for you can technically consider like a kind of linear line because of the fact that we can it's just dividing and multiplying by a factor, which is the same for all of them, so it doesn't matter. So the number of arrangements we don't want is 27 times 20 minus, the number of arrangements that we don't want is 540 minus 108 plus 18. And so this is just equal to, of course, 450. So this means that the probability that we want to find is just simply equal to this number, 1680, minus this number, 450, over this number, 1680. Because this is the number of bad cases. So yeah. So this is simply just, so first we can do is take out the zeros. So this 168 minus 45 over 168. And so this is just 123 over 168. And if you want, you can divide by 3 again to get 41 over 56. Actually, no, you should be dividing by 3, like, if you want. So the final answer is 41 plus 56, which is 97. And in Amy form, that would be 0.97, but that doesn't really matter much. Okay, so it's gone past 6:30. And so I'll just leave this homework problem behind. And so here. So there's an ordered sequence of 36 digits, and we want the property that the sum of the digits to get that adding the digits to get a number and taking the last digit results in a digit not in the original sequence.